Linear programming. In this program, we'll learn how to use linear programming for the purpose of optimization. LP problems are quite varied. And for that reason, what we're going to emphasize in this program is how to identify what all LP problems have in common. First, we'll learn to identify and define the objective function. Also, we'll identify decision variables, or in spreadsheet terms, the changing cells. These cells are going to change subject to some constraints, which also need to be identified. These three parts, the objective function, the decision variables, and constraints, are what all LP problems have in common. By identifying and clearly defining the mathematical model, we then will turn our focus to conveying that mathematical model to solver in order to optimize. Let's look at an example. A cake and pastry shop makes 3 types of cakes, which require 3 significant ingredients. The data for the amount of these ingredients needed to make the cakes are provided in the table below. So this is our given information. And we can see from this given information some important information. First of all, our objective function. We know the profit per cake for each type, small, medium, and large. So the total profit will be $18 times the number of small, $25 times the number of mediums made, plus $32 times the number of large cakes made. We want, as an objective function, to maximize this profit. So our decision variables, or changing cells, will be the number of each type of cake made. Now we have some constraints. The ingredients for each type of cake and the amount of each ingredient is shown. But we have a limited amount of flour, sugar, and cocoa powder. So 8 ounces times the number of small cakes plus 16 ounces times the number of mediums plus 21 ounces times the number of large has to be less than or equal to 400 total ounces available for flour. So these constraints, decision variables, and our objective function have been identified. Now we can shift to our spreadsheet and to Solver to set up our LP model. So in setting up our spreadsheet, we want to use all 3 parts of our LP model and simply convey that information to Excel. So I've added some cells for the profit per cake, $18, $25, and $32 is the profit margin for the small, medium, and large cakes. Now our decision variables need cells also. Right now we're looking at 0 smalls, 0 medium, and 0 large. So this is going to be part of the answer to our problem. We would like to maximize the profit as the number of each type of cake times the profit per cake. Our objective function is to make the result of our profit function a maximum value by changing the number of each type of cake. But we're going to have to do this subject to some constraints. So I have input the ingredient amounts for flour, sugar, and cocoa powder for each type of cake. And then I've added cells to specify that constraint maximum, 400 ounces, 550 ounces, and 150 ounces. Our constraint will actually be that the sum product of our ingredient amounts and the number of each type of cake made has to total no more than 400 ounces. So let's turn to Solver to finish our LP problem. Our objective function is our profit function, and we would like to set that to a maximum value by changing the number of each type of cake made. Now our constraints. We really have three constraints, one for each ingredient. However, we can make this easier to add in Solver by simply saying that we want E13 through E15 to be less than or equal to the total amount available, which are in F13 to F15. So in our Solver tool, this looks like a single constraint, but it's really three. E13 is less than or equal to F13. E14 less than or equal to F14. And then finally, E15 less than or equal to F15. We're also specifying a non-negativity constraint and using our simplex method. Now when I click Solve, Solver is going to find a solution subject to our constraints, and so you can see that Solver used 100% of the available resources. But it was only able to do that by giving us non-integer answers. But we're not going to make 0.3935 small cakes or 0.57 mediums. So we'd like to, either by trial and error, simply changing, rounding up or rounding down the number of small, medium, and large, or we can add a integer constraint. For example, we would like these cells to be integers. So now if we click Solve, the additional constraint of adding the integer constraint gives us integer answers, and we can see that we have a little bit of slack in each one of our ingredients. In other words, none of the constraints, in order to achieve a max profit of $632, none of these three constraints are binding. Now remember, there may be more than one optimal solution. For example, here 3, 18, and 4 also produces the max profit of 632 within the constraints that are needed. So this also would be an option for the bakery in order to achieve max profit. Let's look at another example. Instead of maximizing the total profit, we could also use LP models to minimize the total cost. Here, Sunseal Industries produces two types of raw materials, A and B, and we know the cost per unit of each $4 for A, and $8 per unit is the cost for material B. Now we have some production constraints. These aren't the same as the constraints in the bakery problem in that those were resource constraints, a limited amount of each ingredient. Here, these are some production constraints related to, for example, demand. In this production run, for example, the sum of A, the number of units of A, plus the number of units of B must be a minimum of 700 units. For making material B, we have to have a minimum of 400 units, and we have a maximum. We may not make more than 1,200 units of raw material A. Now, where would these constraints come from? Well, as I said, this could be related to demand, and certainly it's related to costs. If we were to change these production constraints, it's very likely that the cost per unit would change. Now, we do have one resource constraint, and that's time. So 5 hours for B, A is observed to be 5 hours, and for B, 4 hours per unit. And we have a total of 3,000 such hours available. So what we would like is a linear program model that will allow us to optimize by determining the minimum cost needed to produce materials A and B subject to our constraints. So let's look for our 3 core parts of any LP model. First of all, our objective function. It's the same equation. We're using a sum of the products. And this is the same tool, so you can see we also have room for 3, because in the last problem we had 3 different types of cakes. But here there are only 2 different types of raw materials, so we can adjust that. But the cost per unit times the number of each unit is going to be our total cost. And the objective of our problem is to minimize that total cost. So this is our objective function. Our decision variables, or changing cells, will be the number of units of A and B made. Now we have some production constraints. So what I've done is I've first added equals the number of A, or cell B9, and whatever that ends up being, it has to be less than or equal to 1,200. Similarly, C9, the number of units of B, has to be at least 400 units. And the sum of B9 and C9, in other words, the number of A plus the number of B, has to be at least 700. So our production constraints have been set up on our spreadsheet. We just have one more to go, and that is our time. 5 hours times the number of A plus 4 hours times the number of B has to be less than or equal to the total time available of 3,000 hours. So now that we have our model defined and we have added a place for everything in that model on our spreadsheet, we just need to communicate to Solver what we want it to do. So our objective function here is to minimize the total cost. So note that we have marked for our objective minimum. subject by changing the cells B9 and C9. Now our constraints. Our total time has to be less than or equal to the 3,000 hours that we already input. But we have production constraints as well. B9 has to be less than or equal to 1,200. C9 has to be a minimum or greater than or equal to 400. And one more to go. The sum of B9 and C9, which we programmed into our cell right here in C23, has to be a minimum or greater than or equal to 700. Okay, so we are making the unconstrained variables non-negative, or in other words, we have our non-negativity constraint box checked, and we're using our simplex method. Now we just need to solve. And we obtained our optimal solution. The minimum cost is $4,800, and we would achieve that objective function by producing 200 units of material A and 500 units of material B. And you can see that we have stayed within our constraints in order to achieve that total cost of $4,800. However, we can also see that only two of the constraints are binding. In other words, only two have to be just right in order to achieve this solution. And that would be the sum of A and B and the total number of hours used. Let's look at one more example. And in this example, we are given the rate of return, the annual rate of return on different investment options, different areas of the market. And so the 12% return on electronics, 18% on software, 15% in logistics, 12% education, and 17% from retail. These are estimated rates of return for these 5 different market areas. The objective function for this problem would be to maximize our total return using those rates and some constraints. The capital provided will be $5 million. So we're trying to decide how much of that $5 million to invest in the 5 market areas. But we also have some additional constraints. The capital provided, or what we invest in the retail market area, should be at most 40% of our $5 million. The capital for our education market investment should be equal to 26% of the other 4. Logistics should be at least 15% of our mix. The capital allocated for software plus logistics should be no more than the capital allotted for electronics, but it can be less. And the capital allocated for logistics plus education should not be greater than that allocated to retail, but again, it can be less. So we have several constraints, and we can't specify the precise amounts of each constraint until we know how much of our 5 million is invested into each of the 5 market areas. But by using a spreadsheet model, we could specify a cell reference, and once those values are produced or determined by our solver, the constraint value will be known and used to optimize. Now let's go to our spreadsheet to set up our model. So instead of a profit per cake type or a cost per raw material, now we have a rate of return for each of the market areas: electronics, software, logistics, education, and retail. And those are given by the problem. We also know that we're working with a capital investment of $5 million. So in this problem, we're going to have 5 decision variables. How much of the 5 million goes to each of the 5 market areas? So we only have 5 million to invest, and we have the rate of return for each of the 5 market areas. The total return is what we're trying to maximize. This is our objective function. And you can see that this is another sum product. The 12% for electronics times the total capital that we devote from our 5 million to electronics is going to contribute to our total rate of return, and so forth. But the constraints here are a little bit complicated. And before we go to Solver, we want to take our time developing our spreadsheet model, because if we get our spreadsheet model set up correctly, communicating the constraints to Solver will be much easier. For example, we were given by the problem that the total capital that goes into retail has to be at most 40%. So what I've added here is that F11, the amount that will be invested in the retail market area, that is going to be less than or equal to 0.4 or 40% of our 5 million. We were also given that education, or E11, the amount that we invest there should be equal to 26% of the other 4 areas. So 0.26 times the capital to electronics, software, logistics, and retail is going to be the constraint for how much goes to the market area education. 15% of the total capital is the minimum that we want in logistics. So again, I'm using cell references. D11 is our logistics amount, and 0.15 or 15% of our 5 million is the minimum for our constraint. 2 more. Software plus logistics, or C11 plus D11, can be no more than what we invest in electronics. So this is going to be a max constraint, less than or equal to the amount that goes into electronics. And we have the same type of constraint here. Logistics plus education, or D11 plus E11. We want to be less than or equal to retail. So this also will be a max constraint. So now that we have our spreadsheet set up, we have very little information to communicate to Solver. And this is really what we want, is to use our spreadsheet model to make the work that Solver has to do as simple as it can be. What we want from Solver is just to communicate these three core parts of any LP problem. Here, our objective function is to maximize the total return by changing the amount of our 5 million that we invest in each of the 5 market areas, subject to some constraints. Well, the first constraint that I've added is that the total, or the sum, of each market area investment is going to be equal to 5 million. We want to invest all 5 million available. Now we have some other constraints to add. First of all, the amount that we invest into retail has to be no more than 40% of our total capital. The amount that we invest into education has to be equal to 26% of the other 4 market areas. The amount that we invest into logistics, which would be D11, has to be at least or greater than or equal to 15% of our total capital. 2 more. Software plus logistics has to be less than or equal to the amount that we invest in electronics. And 1 more. The amount that we invest into logistics plus education has to be no more than or less than or equal to the amount that we invest into retail. Okay, so we're communicating to Solver only what Solver needs to know. We've checked our non-negativity constraint, and our simplex method of LP is selected. Now we're ready to solve. And here's our answer. The amount that we should dedicate to each of the 5 market areas is shown. And we could see also that all but one of our constraints are binding constraints. The only one that gives us a little bit of slack is this last one, as shown. The maximum total return that we could expect is calculated, and that's certainly a big part of our answer, but the way that we're obtaining that answer is by deciding how to divide up the 5 million across the 5 market areas. So in each of these examples, we can see that by identifying the objective function, the decision variables, and the constraints first, we then can shift our focus to setting up a spreadsheet that has places for all of those 3 core pieces. Once we get our spreadsheet set up, communicating to solver is much easier when we know and fully understand what it is that we're modeling. This concludes the program using linear programming for optimization.